In this video, we're going to teach you everything you need to know about binary numbers for networking. What is this number? Seriously, what is this number? It's 24,356, but you already knew that, because we know how to read decimal numbers as humans. We learned that in the decimal numbering system, each column has a particular value. We have the ones column, the tens column, the 100s column, the thousands column, and the 10,000s column, and it goes on from there. We take the number associated under each column value and multiply it by that value. 2 under the 10,000, so 2 times 10,000 equals 20,000. 4 times 1,000 equals 4,000. 3 times 100 equals 300. 5 times 10 equals 50. 6 times 1 equals 6. We add all those numbers up, and lo and behold, 24,356. Most of us count using decimal numbers, known as base 10. Computers use binary numbering, which is also referred to as base 2. These two numbers are 0 and 1, with a 0 representing an off or a no, and a 1 representing on or yes. Every numbering system has a base. Whether you deal with binary, decimal, hexadecimal, octal, all of those we're not going to cover. We're going to cover a little bit about decimal, mainly binary. Decimal, or base 10. Each of these particular values here is a column. 10 to the 0 power equals 1, because any number to the 0 power equals 1. 10 to the first power is basically 10 times 1, so it becomes 10. Next column, 10 times 10 equals 100, and so forth. The number selection for base 10 is 0 through 9. Binary, or base 2, is a 2-digit numbering system, 0 or 1. We have 2 to the 0 power, 2 to the first power, 2 to the second power, 2 to the third power. Oh, to heck with that. That's too much to go into. I'm going to show you a much simpler way of getting your actual values for your binary or base 2 numbering system. Remember I said that any number to the 0 power equals 1. And you take 2 to the first power, so 2 times 1 equals 2. 2 to the second power equals 4, and exponentially increases. 4 times 2 equals 8. 8 times 2 equals 16. 16 times 2 equals 32. 32 times 2 equals 64. 64 times 2 equals 128. And I'm going to pause right there for a moment, because those values right there, those 8 values, are what we're going to be dealing with later in a binary octet, an 8-bit stream that we use to comprise a subnet address. We continue on with 256, 512, 1024, 2048, 4096, and exponentially increase, basically doubling that number each time because it's base 2 or times 2. Once again, the number selections to represent it are 0 or 1. Converting binary to decimal, we're going to take that 8-bit segment there, and we're going to call that our binary truth table. 10, 10, 10, 10. You don't want to say 10, 10, 10, 10, because 10 is not a binary number. You apply those numbers directly under value table, the column value up above. And then all you have to do is simply add up where you have a 1 turned on, because a 1 is on, a 0 is off. So we add up 128 plus 32 plus 8 plus 2, and we get a grand total of 170. So the binary equivalent of 10101010 equals 170. It's not a binary of 10, 10, 10, 10. Converting decimal to binary is a little bit more complex, and we carry the bit stream out a little bit further there. If we want to take the number 3,824 and put it into binary, we have to first move our column table all the way over to a number that is larger than the number we happen to have. So we went all the way over to 4096. What we do is we go higher than this number, knowing that we cannot exceed that 3,824. But we can take the 2,048, and what we're going to do is we're going to subtract that from the 3,824. So when we do that, we place a 1 under the 2,048, and we subtract it from the 3,824. That leaves us a total of 1794. we look at the next column value over. Can we get 1024 out of 1794? Yes, we are able to do that. We place a 1 there, subtract it, it leaves us with 770. The next column over, can we take a 512 out of 770? Of course we can. That leaves us with 258. Can we get a 256 out of 258? Of course. We do that, we are left with a 2. We come to the next column. Can we get 128 out of 2? No, not even with the best balancing act of the budget. We can't get a 64, a 32, a 16, an 8, a 4. Oh, but we can take a 2 out of that. So we take a 2, subtract it for 2, leaving us 0. And that's what we want to have, is nothing left over. So we have the 4 ones up there and the 5th one over there by the 2. We fill in the rest with zeros. We will not place the leading 0 or preceding 0 under the 4096 because it doesn't matter. It's irrelevant. We only look for the first positive number. So our binary number for 3824 is going to be 111100000010. I'd like to have to say that too many times. We just type it out here, the decimal equivalent and the binary. How this applies to IP addressing. Each of the 4 numbers in an IP address is called an octet. 8 bits in each one of those octets. Here's a decimal equivalent of an IP address that happens to be on the computer I'm using right now, 192.168.10.131. We're going to learn how to apply that and put it into a binary bit stream so that the computer can read it, because the computer does not read decimal. A bit is represented once again as a 1 or a 0. Each octet can have a number ranging from 0 to 255. Binary IP address. We have our binary truth table up there and all the ones that are turned on. If we add them up on the side here, 128 plus 64 plus 32 plus 16 plus 8 plus 4 plus 2 plus 1 equals a grand total of 255. If they were all zeros, the decimal equivalent would be 0. If they're all ones, 255. That's a range of numbers. There's a total of 256 numbers there. Most people don't like to count 0 numbers. The IP address of 192.168.10.131. We're going to break it up by octet. 192. It's represented by 11000000. Should be 2 ones and 6 zeros there for our 8 bits, because 128 plus 64 equals 192, and we don't have anything else left over. That's why they're all zeros. A 168. We apply that. We can take a 128. We can't get a 64 out of what's left, but we can get a 32, an 8, and the rest are all blank. A 10. That's quite simple. Nothing but an 8 and a 2. That makes up 10. And a 131. We have a 128. Nothing for the 64. Nothing for the 32. And the remaining 5 bits are turned on. The computer would read it as this little bit stream here. I'm not even going to attempt to read that right now. The binary subnet mask. Let's say our binary subnet mask is 255.255.255.0. Well, 255 equals all ones, all ones, all ones, and a 0 is all zeros. That's what it looks like as the binary bit stream that the computer reads. The binary address and subnet mask together, we look at it as 192.168.10.131 and 255.255.255.0, its subnet mask. The computer would read it in this fashion right here. Subnet mask values. A number that is not one of the valid values is incorrect and will cause problems in the network if you try and enter it. Matter of fact, the computer won't even accept it, neither will your router. For example, you would never see a subnet mask of 255.255.222.0 because 222 is not a valid number when you line up all the bits for the subnet mask. The values for a subnet mask are quite simple to remember. These accepted values are 0 if you had no bits turned on, 128 if you had the first leftmost bit turned on. If you had the 2 leftmost bits turned on, it would be at 192. As you add a bit, 224, 240, 248, 254, and 255.